we're going to look at some examples here. And the first one, we're going to deal with the number of molecules. The second one, we're going to, of course, deal with the temperature. And the third one will deal with volume. Okay, let's go look at this thing here. And so here's the first thing that we want to look at. We want to look at the first one that we want to look at is we want to look at what are known as the Magdeburg hemispheres. Now, the Magdeburg hemispheres look like this here. They actually look exactly like this. And we have them in the lab, and they're really, really awesome devices here. And so what's special about the Magdeburg hemispheres? Magdeburg hemispheres were first created by a guy who was going to first look at how do I say this, in creating, to sort of like talking about whether atmospheric pressure was strong or not. And so there's a very famous picture, and there's lots of famous pictures of this situation. But the one I'll show you here is that what Magdeburg did is he essentially said this. He went in and he did the following thing. He took horses on one side, and then he had horses on the other side, and right in here, this guy right here is the Magdeburg hemisphere. So what was so important about this during this time here? So what you find here is that when you look at these hemispheres, they're two halves, okay? They're two halves. So what you find here is that it looks something like this here. So if you take these hemispheres, you can actually split them apart. So if I come in here and I start to sort of like draw them here, so when you can split the two hemispheres apart. And the only way that you can do this here is that you have these cups here. So you essentially, you could imagine that there's an end here, and then you have a half of a cup or half of a hemisphere. So in this case, we can say like, okay, here's this half, and then this guy will be this red guy right here. And then there's the other half. So when you do this, you could then, that the only way this is possible here is if there's atmospheric pressure in. So what you're seeing here, they're apart. So you can split the two hemispheres apart if the pressure inside is equal to the outside pressure. And so it's open to the air. Okay, so what you're seeing here is that picture-wise, it goes like this here. So what do I mean by picture-wise? So picture-wise, imagine that I now put them together. And so you could imagine that I have this type of thing. Now, look at the pressure inside, look at the pressure outside. So the pressure inside is pushing out, and then you look at the pressure outside, and it's pushing in. So if the pressure inside equals the pressure outside, then they split apart easily. I mean, you could just tip them over. And so what you're seeing here is that this really implies that there's no pressure difference. And if there's no pressure difference, then that means here is that they do not stick together. And so what ended up happening here is that what this guy did is he did the following thing here. The guy who had the idea of these hemispheres here, Magdeburg is a name of a place, and I don't remember the name of the German scientist that thought this up, but it was like Otto von something something. I don't remember his name per se. I just remember Otto von for whatever reasons here. And so what he does here is that he says that the atmospheric pressure is so strong that if you remove the air, not even 6 horses pulling in one direction versus the other one could pull these things apart. So now here's what Otto von does here. So what he does here is he takes that hemisphere and he starts removing the air. So what happens is that, so Otto von attaches a vacuum pump and what does he do? He removes air molecules. He removes the air molecules. So you could imagine I have my hemispheres now. Okay, so if I have my hemispheres, let's see what the picture looks like now. So what happens here is that as he does this, he attaches a hose, and what he's doing here, he's literally coming in here, and what he does here is he removes air molecules. Now we gotta be careful here, because what's really pushing on the hemispheres, what's really pushing on the hemispheres, which I did not say, is what? Atmospheric pressure. And remember what I said, atmospheric pressure means what? It means that's our high pressure. Okay, that's our high pressure. So if that's our high pressure, what does that do here? Well, what we find here is that it goes something like this here. So now what you're seeing, so when you're looking at these hemispheres, what you're finding here is that there's very few collisions on the inside now. So you could see that the arrows inside are small compared to the arrows outside, which are big. So now inside, you have a low pressure region. Okay, a low pressure region. So removing the air molecules creates the low pressure region. So now what happens? What happens now is that pressure always flows from where? A high pressure to a low pressure region. So then we know that pressure always moves from a high to a low pressure region. And so what that does, the air molecule, so the atmospheric pressure forces these two hemispheres to stick together such that 12 horses cannot pull them apart. So that means they had 6 horses on one side, they had 6 horses on the other side, and they couldn't pull it apart. That's how strong atmospheric pressure is. But again, what created that low pressure region? Removing the air. That's what the ideal gas law does, right? That's what the ideal gas law does. And so, we could, and a very similar thing happens with tires too. So what happens with tires? When you add air at a gas station to your car tires. What happens when you add it? So what you're really doing here, right? So if you could imagine that, let's say that this is the ground, and what we're going to do here is that you have a low tire. So if you have a low tire, I could imagine that you have maybe a tire that looks like this. So it's a little bit flat here. So what you do here in this case is that there's air in the tire. And so when you're looking at the air in the tire, what you're finding here is that there's collisions with the walls of the tire. Okay, so if you now add air, you're going to have what? You're going to have more collisions. And if you're going to have more collisions, you're then going to have what? You're going to have a higher pressure. And so what happens next then, because you've done that, then what you're seeing here is that you're getting your tire is now going to do what? It's actually going to be slightly bigger. And it's going to be slightly harder because now you're not adding kinetic energy to the gas molecules. You're just adding more gas molecules to do this. So now you have more collisions in this case here.